So class started off, you saw, we talked about this at the end of last week, when you're doing area under a curve, when you're approximating the area under a curve with rectangles, that using more rectangles is going to give you a better estimate. And whether you use right hand, so I'm just, again, this is a lot to write down, so don't necessarily try to copy this all down. It's more important we do these examples, but just to state where we are, if you use, let's say, the area under a curve, remember R8 stands for right-hand endpoints with 8 rectangles. You put them under the curve, find the area of those 8 rectangles. You're going to get an approximation that is an overestimate, and your error is how much those rectangles, each one of those, the total sum of those areas that are extending above the curve. If you use more rectangles, here I have a picture of what an L16 approximation would look like. Left-hand endpoints this time with 16 rectangles, and you are going to get an underestimate. And the error in this approximation is how much those rectangles don't quite go all the way up to the function. All of those little tidbits of area in sum would be your error. And so the ideal situation would be to use as many rectangles as possible. And we talked about it last week. You talked about it just a few minutes ago. That would mean an infinite number of rectangles. So either way, right, the formula for the area is you're going to be adding up a bunch of heights, which would be given by the value of the function at these numbers. So these are your heights. This is all your heights. And delta x, of course, is your width. That's the area of a rectangle. And you could write this in summation form. So for this example right here, with only 8 rectangles, you could say this is the sum from I equals 1 to 8 of f of x sub I times delta x, right? F of x1, f of x2, f of x3, all of those times delta x. And there's a little bit of, I even had a hard time reading this book to really understand what some of the notation they use. Because if you use left-hand endpoints, and let's say I had the same numbers here, right? And so your left endpoint, you can call that A, your ending value B, or if you started with x1 here, I guess you can call that x sub 0, right? If you used left-hand endpoints, then you would be using x sub 0 as your first height, and then x1, and then x2. And if you had 16 rectangles, you would be stopping at 15, x sub 15, right? Because you're going to go across. So there is a slight difference in that when you use left-hand endpoints, you still have 16 rectangles, but where do you start? You don't start at x sub 1 and you don't end at x sub 16. You start at 0 and end at 15. So if you think about it, it's f of x sub I minus 1 times delta x, right? When you get to 16, that's going to be x sub 15. So there's a slight difference when you're using x sub I, that stands for right endpoints. X sub I minus 1 is left endpoints. Of course, we've talked about midpoints, but we're not going to really get into that so much when we start to go for the exact area. Okay. If you're just joining us, you've already talked through this. So I'm going to go through this kind of theory part really fast because I think it's more, I'm going to guess from what I saw in the lecture, you're more interested in seeing another example like that long integral problem, trying to evaluate it. So we will do that. To get the exact area, you can use any of the methods, right? As long as those rectangles get infinitely thin, whether you use right endpoints, left endpoints, midpoints, it doesn't really matter if there's an infinite number of rectangles, which was what this blank was for. You need to use an infinite number of rectangles. And the way the book notation is, this took me a while to figure out when they were doing this. When they write x sub I star, that means it doesn't matter. You're using either right, left, or endpoint. So this x sub I star here is when they're talking about either of these, right? Either or either, any one of those, either choice for your, remember, it's more terminology, but what we call those numbers are sampling numbers, the numbers you choose to determine the heights of the rectangles. I think I used that before, so I'll go ahead and write it. Sampling numbers. Okay. That's maybe a little bit better. There we go. And if you do that, whether you use left, right, midpoints, and you somehow find a way to add up an infinite number of rectangles, so you take the limit of this, that's what we now are going to define as the definite integral. This would be the definite integral from some, whatever your left endpoint is, x equals a to x equals b of f of x dx. So this right here, you would refer to that as, I don't think I ever defined this, but I think you did this in class. When you're doing a summation of f of something times delta x, f of x or whatever, that's called a Riemann sum, to give credit to the mathematician who thought of that, I guess. And this would be the limit of a Riemann sum, right? You're doing the extreme case when you have an infinite number of rectangles. That's the limit of the Riemann sum. By definition equals, we're going to now refer to that as the definite integral of f of x from x equals a to x equals b. It's the exact value of this, exact value of that limiting Riemann sum, which can give you area under a curve, but only if your graph is entirely above the x-axis. I've been referring to these, I did at the beginning, as finding the area under a curve, but this will give us the area only if our function is above the x-axis. We'll talk more about that in a second. If you're, I don't know if you're talking about for me or for well, probably for me. Well, I have it all recorded. So, and these are just handwritten pieces of paper. So you go back and look at it. The other thing is, if you looked at my website too, a lot of these notes are basically straight off my website, because once I find examples that I think kind of work, there's no reason to do different ones. So, and actually, based on what I saw in class earlier, I'm going to make this one a little trickier. I want to prepare you for the worst. Let's use the limit definition of the definite integral to evaluate this integral 2x plus 1, let's say from 1 to 3. Instead of 0 to 3. I've got another one that starts at 0. And so I am going to put note, if f of x is greater than or equal to 0, in other words, if it's above the x-axis, above the x-axis, for the entire interval, then the integral will give us the exact area. The integral will give us the not just an approximation, the exact area. Now, this will actually, what I'm going to do will actually help maybe for what I saw right at the end of class. She wanted to give you some examples. And what those examples, I don't know how many she did, but what those examples were meant to show, okay, let's say 1, 2, this is 3. So this part, don't worry about this. We want to find this area. That's what that integral is giving us. And in some cases, You don't need any fancy calculus to find this area. What shape is this area? If I ignore this part right here, what shape is that? Most people might recognize it more if it was turned sideways, if it was turned like this. Do you recognize what that shape is? Yeah, it's a trapezoid, huh? That's a shape of a trapezoid. And you probably remember a way to find the area of a trapezoid because that's really all this integral is going to represent. And if you don't, it's okay, because a trapezoid could be broken up into, you could think of this as a rectangle and a triangle, right? We don't need to remember the formula for a trapezoid. We just break that up. So what I wanted to do here was let's find the area using geometry, and then I'm going to show you how to do it using the limit definition that you worked through in class today. So you can see, so for number one, we can confirm that it's working, that it's giving us the right answer. Okay, so let's start here. What is, to find the area of this rectangle, I need to know the length. This length right here from 3 to 1, I know that that distance is 2. I need to know this height right here. And to find that height, I could just plug 1 in for x, right? 2 times 1 plus 1, that gives me 3. So the area of just this rectangle right here, 3 times 2, I know that that is 6. And then I need to find the area of this triangle. Well, I already know this dimension right here is 2, right? That's the same. This is 2. What I need to find is just this part right here. But what would this total distance be right here? That's just the value of my function when x is 3. And 2 times 3 plus 1 would give me 7. So if I already know from here to here is 3, because that's the same as this, what does this have to be? Is everybody okay with this part right here would have to be 4, right? Good. So then the area of this triangle right here, remember the area of a triangle is 1/2 base times height. Base times height is 2 times 4 is 8. Half of that is going to give me 4. So I'm going to put underneath here, then the integral will give us the exact area, and I'm going to put which we found to be 6 plus 4 should be 10. So now obviously that wasn't too hard, right? And what you saw in class for about 15-20 minutes evaluating a definite integral using the definition can take a lot of time, right? So one point of that, one takeaway is, as we get deeper into integrals, if you see a way, if you realize that this integral just represents this area, and you see that just using some geometry would be faster, by all means, do it that way, right? It's going to be much faster. But then the second thing now is I am going to show you how to do this using the limit definition of the derivative. And if I don't get 10 as my final answer, something's wrong, right? Because the area has to be 10. But let's now do it. So now that was going to be an L. Let's use the definition of the integral. And to do that, I'm going to redraw the picture just because I think it helps to, draw this kind of big. So here's my line. F of x equals 2x plus 1. We want to find the area from, and this isn't drawn to scale, that's okay. This is 1, this is 3. This one, remember the left-hand number you usually call A, this one's B. So we want to find this area. Okay. Now, I don't know, I was kind of doing other things at the same time. I know that Dr. Burke talked about how you can use left-hand endpoints, right-hand endpoints, midpoints, as long as you have an infinite number of rectangles, it doesn't matter. However, given the choice, and you did see, I saw in lecture, she started one with left-hand endpoints, and somebody wrote in the chat, hey, if we used right-hand endpoints, wouldn't it be instead of I minus 1, it would just be I? And she did it that way. And some of you may have noticed that the formula she ended up with looked a little bit simpler than the one using left-hand endpoints. So given the choice, unless you're directed otherwise, always choose right-hand endpoints. Choose right. It's almost always faster and easier. Choose right-hand endpoints if given a choice. If it says set up this integral using left-hand endpoints, then I guess we have to go there. So then here's the idea. Starting at 1. Now I know I have to fit an infinite number of rectangles, but if I make them infinitely thin, we're not going to see anything. So I'm going to give these rectangles some legitimate looking width, but then we're going to have to imagine that we're taking the limit as n goes to infinity, so they're actually getting infinitely small. So let's draw some rectangles in using right-hand endpoints. And remember how it works. That very first number I would have chosen here, this would be x sub 1, this would be x sub 2, this would be x sub 3, and so forth. And we know from our Riemann sum that if we take, this time we want to put n rectangles in here. So there's going to be 1 to n. And we know that if we add f of x sub I, that'll give us the heights of those rectangles, and then multiply that by delta x. That's the width. And then later on, we'll take the limit as n goes to infinity. But let's worry about, let's put n rectangles in there right now. So what is our formula for delta x? I'm going to do that over here. Delta x is b minus a over n. So that is going to be 3 minus 1 over n, which is 2 over n. 2 over n. Right? We don't have a, it's going to look like that when we're using n rectangles. You know, when you were doing it with 4 rectangles or 6 rectangles, then you actually get a fraction, but it's going to be 2 over n. So we have a formula for delta x. Now there is a formula for x sub I, but it's pretty easy to figure out. Think about it this way. Oh. Yeah, that's a great observation. If you did midpoints with a straight line, think only if it was a straight line, if you did midpoints, you would get the exact area, no matter if you used 1 rectangle or 100 rectangles, it would be the exact area. Yeah, that's right. It's a good observation. What trouble will be when we get into like curve graphs, then that wouldn't be true. Okay, so what we need now is a formula for x sub I in terms of n. So think of it this way. We know what delta x represents. That's this distance, delta x. This is delta x. This is delta x. So how do I get to x sub 1? To get to x sub 1, I start at 1 and I just add delta x, right? It's this plus this gets me to x1. So I start at 1. To get to x sub 2, I start at 1 and I go, how many delta x's? 1, 2 delta x's. So that's 1 plus 2 delta x. X sub 3, you start at 1, you go 1, 2, 3. That's 1 plus 3 delta x. So the idea is you're supposed to then come up with a formula. Well, what would it be if I was on some random rectangle? If I was on my ith rectangle, if I was on x sub I, what would the formula for what would be the location of this x value? It would be 1 plus I. See how that fits the pattern? X sub 2 is 1 plus 2 delta x. X sub 3 is 1 plus 3 delta x. X sub I is 1 plus I delta x. And your general formula for x sub I is always going to be a plus I times delta x. This is bubble worthy here. This is only for right endpoints, but I told you that's going to be the best one to do anyhow. So we'll bring the limit in later. Let's find a formula right now in terms of n. So we want to do f of 1 plus I times 2 over n, and then multiply that by delta x, which is 2 over n. That's an I. And if it's okay with you, isn't this the same as I plus, no, not I, 1 plus 2i over n? Can I just call it that because it looks a little better? 1 plus 2i over n is the same as 1 plus I times 2 over n. Okay. Now, how do you do if my function is 2x plus 1? What would f of 1 plus 2i over n do? How do you do f of anything? If my function is 2x plus 1 and I say, what's f of 7? What do? You plug in the 7 for the x, right? So if someone, I know this looks weird, but if you're asked to do f of 1 plus 2i over n, you're just going to put that in for this x. That's going to be 2 times 1 plus 2i over n plus 1. Just putting that in for x. And that whole thing now is going to get multiplied by 2 over n. And then let's simplify this a little bit, and then we'll bring the limit in. So if I distribute this 2, this is now 2 plus 4i over n, and then I have this plus 1. And then I could combine these two here. So that's really 3 plus 4i over n times 2 over n. And then lastly, let's go ahead and distribute this. I'm going to have to move on to my next piece of paper here. So if I do 2 over n times 3, that's going to give me 6 over n, and then 8i over n squared. And at this point, here's what you're going to want to then keep in mind. Remember that we have those formulas. In particular for this one, I believe it was Friday, we decided that the sum of the numbers from 1 to n, which is the summation from 1 to n of I, remember that's 1 plus 2 plus 3 plus 4. Remember Gauss's problem? That equals n times n plus 1 over 2. And there's another one for I squared if we need it. So do you see that that's in here, right? I've got a summation from 1 to n, and there's an I sitting right there. So what I want to do is use my properties of summations that we went over on Friday. One of them being that if I want to add this plus this, I can split these up into 2 separate summations. And the other one being that anything that's constant, remember this, you can pull the constants out in front. Now, what do I mean by a constant? We're used to seeing that, well, n's not a constant, but think about who's changing here. As this counter goes, I becomes 1, I becomes 2, I becomes 3. Who's stayed? 8 over n squared never changes, right? It's only things that would have I in it that change. So this 8 over n squared, I could always factor that out. And that's just going to leave me with the summation of just I, which I have a formula for, right? And you kind of, this is a constant too, right? There's no place I ever goes in here. So what I like to do is I just factor that out too. I'm just going to pull that out in front. And that's just going to leave me with a 1 there. And we're almost done. Let's start with, I think maybe the obvious one is this right here now gets replaced with n times n plus 1 over 2. We'll deal with that in a second. And then, does anybody remember, what does this really mean? What is that telling us to add? This is telling us to add, when I is 1, it's telling you to add, yeah, it's going to be 1n, because it's telling you to add 1, and then I becomes 2, 1, plus I, another 1. It's telling you to add 1 to itself n times. So this is just 1n. This is just becomes 1n, or just n. Okay, we don't have any more summations. So the last step would be, besides, we might as well just cancel that in and out with this one. Now would be a good time, since we agreed we'd have to have an infinite number of rectangles. We are now going to take the limit. So I'll put now let n approach infinity. These guys just canceled out, so that's just 6. Now to sort this part out, you could simplify some things, but maybe we'll just do this. Let's distribute this. And isn't it true if this is like 8n times n, this would be 8n squared plus, if I did 8n times 1, that would be 8n. And if I just combine the bottom, that is 2n squared. And at this point, this is 17b. You've already been assessed last quarter how to do limits to infinity, so that if you already know from what you learned in 17a, if you can already tell me what this approaches when n goes to infinity, you don't have to show any work on that anymore. That was last quarter. Who knows what's the limit of this part right here? And remember, I'll remind you that in the world of infinities, who determines the limit? It's the biggest power on the top and the bottom. Remember that from last quarter? And who's generating the biggest infinity on the top and the bottom? Well, on the top, you've got n squared versus just n. So this doesn't really matter so much, right? It's going to come down to these two terms. And the ratio of 8n squared to 2n squared is 8 over 2. This is going to approach 4. So I'm just going to put an arrow through. This whole thing approaches 4, which is 8 over 2. Hey, if you felt a little rusty on that, what could you always do on this? If you have an infinity over infinity limit, you could do a L'Hopital's rule on that too, right? Either way, you're going to get 4. Or you could divide everybody by the biggest power of n, right? You'll see that you're going to get 8 over 2 as well. So any option is fine. I'm just saying you don't have to do any of that work. If you know that limit's going to be 4, that should be fine. And my answer then becomes 6 plus 4, which, what do you know? Calculus actually worked. Because that's exactly what we were expecting the answer to be, right? We were expecting it to be 10. I got a question. How do you know which summation formula? Well, you'll see. There's an answer to that. That's a good question. Did you notice in this problem that my function that I was doing the integral for just had x to the first, right? It was 2x to the first plus 1. And what ended up showing up, what formula did I end up needing at some point was the formula for I to the first. Guess what would happen, and I've got one coming up here. Guess what would happen if I had an integral with an x squared? At some point in this process, you're going to end up with that formula. And you may remember there's a formula for that. And so we'll get to that. We've got another one. Okay, let's see, that took a while just doing that. I have one more, like I said, but here's what I want to say. That process took a lot of time, right, to actually use the limit definition. I know your quizzes are not super long. So if you got one of these on the quizzes, on a quiz, I don't think it would be anything more difficult than this kind of a linear function. Okay, because these problems take a lot of time. I think you should know how to do them, but that's so don't be surprised if, and you have some homework on this, or you will, I think. You will get homework on this because these are from the book, where you don't necessarily need to do the whole thing to evaluate the definite integral, but some of the problems in the book just tell you, here's a limit that looks like a Riemann sum. Just tell me what definite integral this Riemann sum was trying to would evaluate actually. And this is very, very easy. These types of problems, way easier than what we just did. You just have to recognize that this is describing some kind of an integral from a to b of some function dx. Okay, and so, and then the other thing, that you see the x sub I stars, that means somebody was writing an integral using the limit definition, and it didn't matter. They were using right endpoints, left endpoints, midpoints. It doesn't really matter. So basically, you want to think of, well, for one thing, this is a whole nother conversation, but it's not a coincidence that your delta x and your dx, those mean the same thing. When you, where is it? You know how delta x represents a width of a rectangle, that one, the one we just did? If you took an infinite number of rectangles, those delta x's, each delta x gets infinitely thin. So that dx literally does represent an infinitely thin rectangle width. When we make it infinitely thin, it's really just dx. And so that must mean then this part right here must be your f of x sub I star, I guess. And so just think about what's been done to x sub I star. Well, it was 2 times x sub I star plus x sub I star squared, the square root of that. So not surprisingly, this integral is just the square root of 2x plus x squared, just like this, dx. And if they give you a interval width, this is your a, that's your b. It's just that integral from 1 to 8. That's it. They don't want you to evaluate it. They just want you to know that this limit represents that definite integral. Here's another one. This one's number 17. In class, she did number 16 and 18. I was like, perfect. I was going to do 15 and 17. So they try to mess with you a little bit with the notation. Like the previous one had x sub I star, whereas this one just has x sub I. Don't worry about that, because remember that if n goes to infinity, it doesn't matter if somebody used midpoints or left endpoints or whatever, it's going to give you the exact integral. So, don't worry that it doesn't have the star in there. This is still your f of x sub I. That's still your dx. Your interval is still your a and your b. So this whole sum, whole long crazy looking mess just represents the integral from 2 to 6 of x times the ln of 1 plus x squared times dx. That's it. Okay, so it could be that easy, right? It could be that easy. That would be great. on a quiz or a test. I'm looking at the clock here, seeing I have some time here, but I want to make sure I get this example in here. So I was hoping to show 2 of these. So let's go back. Let's do one more definite integral using the limit definition. And once again, since nothing was specified, we are going to use right-hand endpoints. I might come back to this example. So same strategy. Now here, what's different is this is a portion of a parabola, right? Y equals x squared minus 1 is a parabola shifted down 1. So I only showed like the portion of it that we're concerned with going upward here. And so the idea is we're going to use n rectangles first, use n rectangles. Eventually, we'll let n go to infinity. Our formula for delta x, still the same, b minus a over n. So that's 1 minus 0 over n is 1 over n. And remember what I told you for right-hand endpoints, your x sub I is always going to be a plus I times delta x. This time our a is 0. It's a b on the top. A is always your lower limit. So in this case, it's just going to be 0 plus I times 1 over n, which is just I times 1 over n is just I over n. And then I just like to draw these out just so I see what I'm doing. This would be, I'm going to call this x sub 1. I'm going to have a rectangle going to my function. Notice this time, for the first time, anything we've done in here, it's the rectangle's always been going up, but this is going down. That would be x sub 1. This is x sub 2 using right-hand endpoints. X sub 3 and so forth. Our Riemann sum is the summation from 1 to n f of x sub I times delta x. So we have to do f of I over n times delta x, which is 1 over n. Sometimes, I mean, it depends. I would defer to what Bert does. Eventually, you're going to take the limit. You could bring the limit in right now if you want to. I just find, as you saw, there's a lot of work. I just like to simplify this and then at the end, let n go to infinity. So saves a little bit of writing. My function is x squared minus 1. So what is f of I over n? I'm going to put that in for x. It's going to be I over n squared minus 1. X squared minus 1, and then that gets multiplied by 1 over n. And then I just simplify it. So this is I squared over n squared. You know what this is kind of like, by the way? Remember the limit definition of the derivative? Remember when we had to fight through that last quarter where it was like, f of x plus h minus f of x all over h, and do all the algebra to solve those, the limit definition of the derivative. This is kind of the equivalent for 17b. Don't worry. All this fancy summation stuff is going away very soon. We're going to find a shortcut for this coming up. But just like last quarter, I like to think you don't appreciate the shortcuts until you actually had to do something the long way, right? Then you're like, oh, I'm so glad to have this shortcut. So this is temporary agony. We're going to distribute this 1 over n. And now, you know, as you start to see some of the steps, you can combine a couple. I'm going to distribute this, and because they're going to be two separate terms, I'm going to break this up into two separate summations. So I squared over n squared times 1 over n is going to be I squared over n cubed, and then I'm going to subtract this times 1, which is just 1 over n. And then, yeah, so as I hinted before, keep those formulas in mind. We know there's a formula for the summation of I squared. And anything with n in it is a constant because it's only I that's changing. So I'm going to pull out, I think it's just easier to see this way. I'm going to factor out 1 over n cubed so I can isolate the summation from 1 to n of I squared. And just like I did on the last one, I like to also pull out over here. So I'm just left with 1. And I was pleased to hear, because when other people teach 17b, they force their students to memorize these formulas. And I just, I don't see the point in memorizing it. But does anybody know? The formula for the I squared is n times n plus 1, 2n plus 1, all divided by 6. And then we already talked about this one. This is just adding 1 to itself n times. So that's just going to equal n. And then, well, besides canceling out those n's, now that we see they will cancel out, the last step is to take the limit with what's left over. And here's something that I think you could also expect to be able to do and not have to show every single step. We've done a lot of work already to get to this point, right? Knowing that when you take the limit as n goes to infinity, who do I focus on? The smallest power of n or the biggest power of n? When n goes to infinity, who determines the limit? Yeah, it's the biggest, right? It's the biggest one. So if you were to FOIL this all out, I don't really want to, but if you were to FOIL it all out, what's your biggest power of n going to be? N to the first, n to the second, n cubed, n to the fourth. If you were to FOIL out all three of those terms. Yeah, how many people can tell it's going to be n cubed, right? Because I have n times another n. And then more specifically, thank you, what would be your coefficient? How many people agree it's going to be 2n cubed plus some smaller values of n if I were to multiply that all out, right? Whereas in the bottom, I have 6n cubed. That's it, because it's just this times this. And then, of course, these guys cancel, so it's just minus 1. What is this limit going to approach right here if you reduce that fraction? How many people agree with 1/3? Good. I'm seeing a bunch of 1/3. Yeah, it's going to be 2 over 6. So this part right here approaches 2/6, which is 1/3. 1/3 minus 1 gives me a final answer of negative 2/3. Negative 2/3. Now, I didn't stick around for the last problems when she was using geometry and stuff to do those, but I don't know. So I don't know if you had this discussion, but that might bother you. That might bother you, this final answer, because I've been certainly guilty of saying this. When we've been doing these approximating rectangles, what have we been using it for? To estimate the area, right? The area under a graph. Well, that was true. That was true whenever my function was above the x-axis. But obviously, area can't be negative, right? There's no way that the area could come out to be negative 2/3, right? Sorry, I'm having trouble fitting this all in here. So we got an answer of negative 2/3, but that cannot be the area, right? Note, area must be positive, right? So there's no way that that could be the answer to the area under the graph. So here's what's going on, and you need to know this about integrals. I'm going to slide this back up on my picture here once you write that note down. In truth, when you do a Riemann sum like this, it doesn't necessarily give you area. All it gives you when you do a Riemann sum is it just gives you the limiting value of this expression, right? That's all you're doing when you do a definite integral. And here's the problem. Think about this, like when you do f of x sub 1, what kind of a number are you getting, right? This is the same as f of x sub 1 plus f of x sub 2 plus f of x sub 3, all of those values times delta x. Delta x is a positive value, right? That's a whatever this distance is. But do you see that all of these are actually coming out to be negative, right? Because when you plug it into the function, you're getting a negative value for the function. So what that means is, this is a big note here. Note. The integral of a function, which is our limiting, gives area when, I already wrote this down, when f of x is greater than or equal to 0. If f of x is less than 0, then the integral comes out negative, Okay. Now, if you had to make a guess what the actual area is back up here, what do you think remember, area has to be positive. When we evaluated our Riemann sum, when we did the definite integral, we got negative 2/3. What do you think the actual area probably is? Yeah, it would be 2/3. And how I would know that is because the entire function was negative. So I was adding up, even though it came out to be negative, I was in some ways capturing area. It just came out to be negative because it was below the x-axis. So the actual area would be positive 2/3. The trouble arises when you start looking at graphs where part of the graph goes above the x-axis and part of it goes below, right? Like if I had a function, where it went something like this, let's say this was A and this was B. If I tried to do the integral from A to B of f of x dx, what would happen is this part of the integral would come out to be positive. This part right here would come out to be negative. And because there's more negative area, so to speak, as positive area, I'm pretty sure this integral would come out to be negative. But what would the actual area of this red shading be? It would be really hard to determine if you just did it that way, okay? But it is important to know that when a graph goes below the x-axis, the value of the integral is going to turn out to be negative. If I could maybe squeeze, I know I'm over time here, but just this might help really solidify that argument or that idea. So say you were asked to evaluate the integral from -2 to +2 of x cubed. If you think about the graph of x cubed, x cubed is a great example of an odd function. You may remember studying those. And one of the characteristics of an odd function is it's symmetrical about the origin. And so if you were to do the integral from -2 to +2, you can kind of imagine putting those rectangles in, right? However they come out, they would be this part right here would come out to be negative, but your rectangles here, if you did a Riemann sum here and took the limit of it, this part here would come out to be positive. And what do we know about a graph like x cubed is these two parts are actually symmetrical. So what do you think the final answer would be? Exactly. These guys would balance each other out because of the symmetry of x cubed, and this integral would have to come out to be 0. Now, of course, what I'm not saying is area speaking, this area plus this area does not equal 0, right? Area has to be positive. It's just when you do the integral, it would come out to be 0. Okay. Because of that thing of this part being negative. So more on that on Wednesday. I'm keeping you long enough, especially since most of you came through a pretty challenging lecture already. So yeah, take a break, get some lunch if you haven't eaten lunch. Yes, I will stop recording here.